Polar molecules. A polar molecule is a molecule that has a partially positive and a partially negative end. So if this represents our molecule, part of it is a little bit positive, part of it is a little bit negative. A molecule is polar overall if it contains a net dipole. A net dipole is a result of the sum of the individual dipoles due to polar covalent bonds. So you must contain polar covalent bonds if you are a polar covalent molecule. So polar molecules must contain at least some polar covalent bonds. If you contain just nonpolar bonds, you will be a nonpolar molecule. And we talked about polar covalent bonds, where they are on the bonding continuum. So if you are between 0.5 and 1.7, on the bonding continuum, which is using differences in electronegativities, then you have polar covalent bonds, therefore you can be polar. So for instance, carbon hydrogen bond. This has a difference of electronegativity of 0.4 because it's 2.5, the highest one, minus 2.1, the lowest one, which is 0.4. So if you contain just CH bonds and CC bonds, you're nonpolar. However, a CO bond has a difference of electronegativity of 1.0. Oxygen minus carbon. So this is a polar covalent bond. To draw polar covalent bonds, you draw an arrow pointing in the direction of the atom with the strongest electronegativity. The electrons are being pulled in that direction, leaving a slightly polar end. So the head of the arrow, the arrowhead, is the little bit dipole, and the tail is the little bit positive. So let's take a look at an example. Let's do ammonia. So we need a Lewis structure first. So nitrogen brings 5 electrons. Each hydrogen brings 1. for a total of 3, so we have 8 electrons to place. So put in your 3 bonds to hydrogen. We've used 6 electrons, so we have 2 electrons to place. The hydrogens are satisfied. They have their 2 in this hydrogen-nitrogen bond. So 2 electrons go on the central atom to complete nitrogen's octet. Now, dipoles. So our structural diagram will look like this. Difference in electronegativity. So nitrogen has electronegativity of 3. Hydrogen is 2.1. So the difference is 0.9. So we do have a dipole. Hydrogen has the weakest pull. So our dipoles are going to be towards nitrogen. Okay, so dipoles add like vectors. You take the tail of your dipole and your head of your dipole, and you add them together. So your second dipole, the tail of it adds to the head of the first dipole. So we're just going to randomly say that this dipole is dipole 1, this is dipole 2, this is dipole 3. So our first dipole goes in this direction, 0.9. Our second dipole goes in the opposite direction, and it's equal in size, 0.9. So we're basically back where we started, because these are right on top of each other, but obviously I can't draw them like that. Then our third dipole goes up from where our second dipole ended up. So we actually end up with a net dipole because we are not, our finish is not at the same place that we started. So if you end up, the head of your last dipole is not where you started, you are a net dipole. So we have a net dipole going towards nitrogen. Therefore, this is a polar molecule. We take carbon dioxide, Lewis structure and structural formula. The difference in electronegativity between carbon and hydrogen is 1. So we have 2 dipoles, both pulling away from carbon towards oxygen. When we add these 2 vectors together, or these 2 dipoles, let's say this is dipole 1, this is dipole 2. We go in that direction 1, we go back in that direction 1. Because we're back where we started, there's no net dipole, and this is a non-polar molecule. So even though it contains polar covalent bonds, it is non-polar overall. Now, if you take a look at Table 3 on page 85, it actually lists the types of molecules that are polar and the types of molecules that are nonpolar. You'll notice that the nonpolar category is a lot smaller. And basically it can be summarized in this way. Your nonpolar if you're a diatomic element, so you have the same two elements in your molecule, so your difference in electronegativity is 0, so you're pure nonpolar. So these are your, for instance, your diatomic elements. There's 7 of them. And you're also nonpolar if you are carbon bonded to only one other type of element, and there is an even number of that element. So for instance, carbon dioxide. Carbon is bonded to one other element, the oxygen, and there's an even number, so this would be nonpolar. Carbon monoxide is bonded to one other element, but it's an odd number, 1, so this one is polar. CH4 bonded to one other element, hydrogen. 4 is an even number. That would end up being nonpolar. CH3OH, methanol. Carbon here is bonded to 2 other elements. Therefore, it's polar. So all of these that are polar end up with a net dipole. Those that are nonpolar either have a difference of electronegativity less than or equal to 0.4, or their dipoles cancel. Pretty much everything else will be a polar molecule. What I want you to do right now is decide amongst yourselves which one of these molecules are polar and which ones are nonpolar. Take a minute to do so. And pause this video. Okay, so diatomic elements, carbon bonded to only one other type of element and an even number. So these are the non-polar. Everything else would be polar, would have a net dipole based on the table. So I'd like you to read page 82, 85, and attempt questions 1 to 4 on page 84, and questions 5 and 6 on page 85. What I'd like you to do also is to go back to your modeling lab that you did yesterday, finish it up, but I also want you to put in dipoles, if they exist, on your structural diagrams. So structural diagrams. Put in bond dipoles and indicate somewhere on that line for that molecule. Maybe it's in the margin, maybe it's in the same box as your structural diagram. Whether or not, I want you to explain, or identify rather, whether or not that molecule is polar or nonpolar. And have a fabulous weekend.